Benchmark for zero-shot evaluation of information retrieval models. Information retrieval (IR) models have often been studied in homogeneous and narrow settings, which has considerably limited insights into their out-of-distribution (OOD) generalization capabilities. To address this, and to facilitate researchers to broadly evaluate the effectiveness of their models, we introduce benchmarking IR, B, a robust and heterogeneous evaluation benchmark for information retrieval. We leverage a careful selection of 18 publicly available datasets from diverse text retrieval tasks and domains and evaluate 10 state-of-the-art retrieval systems including lexical, sparse, dense, late interaction and re-ranking architectures on the B benchmark. Our results show BM25 is a robust baseline and re-ranking and late interaction-based models on average achieve the best zero-shot performances, however, at high computational costs. In contrast, dense and sparse retrieval models are computationally more efficient but often underperform other approaches, highlighting the considerable room for improvement in their generalization capabilities. We hope this framework allows us to better evaluate and understand existing retrieval systems, and contributes to accelerating progress towards better robust and generalizable systems in the future. B is publicly available at https://github.com/ukplab/b. 1. Introduction. Major natural language processing (NLP) problems rely on a practical and efficient retrieval component as a first step to find relevant information. Challenging problems include open domain question answering, 8, claim verification, 60, duplicate question detection, 78, and many more. Traditionally, retrieval has been dominated by lexical approaches like TF-IDF or BM25, 55. However, these approaches suffer from lexical gap, 5, and are able to only retrieve documents containing keywords present within the query. Further, lexical approaches treat queries and documents as bag of words by not taking word ordering into consideration. Recently, deep learning and in particular pre-trained transformer models like BERT, 12, have become popular in information retrieval, 37. These neural retrieval systems can be used in many fundamentally different ways to improve retrieval performance. We provide a brief overview of the systems in section 2.1. Many prior work train neural retrieval systems on large datasets like natural questions, NQ, 34, 133K training examples, or MS Marco, 45, 533K training examples, which both focus on passage retrieval given a question or short keyword-based query. In most prior work, approaches are afterward evaluated on the same dataset, where significant performance gains over lexical approaches like BM25 are demonstrated, 15, 31, 46. However, creating a large training corpus is often time-consuming and expensive, and hence many retrieval systems are applied in a zero-shot setup, with no available training data to train the system. Contributions made prior to joining Amazon. Preprint. Under review. Fact-checking Fever Wiki Query Natural Claim Docs Wikipedia Articles DUP. Question retrieval Quora Query title Quora Wikipedia articles SCI Fact Scientific Query Scientific Claim Docs PubMed articles StackX Docs Argument Retrieval Tush 2020 MISC Docs SIDX Scientific Query Article Title Docs PubMed Articles Query Natural Query Docs Wikipedia Articles args.me Arguments News Retrieval Trick News IDBate Arguments Query News Headline Docs News Articles Robust 04 Query Argument Docs Query Scientific News Query Docs News Articles Docs Wikipedia Articles Scientific Query Biomedical Query Docs PubMed Articles FIQ 2018 NF Corpus Query Financial Query Finance Docs Investment Articles Tweet Retrieval Signal 1M Scientific Docs Twitter Tweets Query Nutrition Facts Docs PubMed Articles Entity Retrieval DBpedia Query News Headline Twitter COVID-19 Query Cord 19 Articles Docs BioASQ Query Multihop Query Wiki Argu Animisk Biomedical IR Trick COVID Hotpot QA Query Title and Body Query Controversial Query Citation Prediction Wiki Quora Questions Query Query Title Query Climate-Based Claim Docs Question Answering NQ Cadupstack Climate Fever Wiki 9 Tasks 18 Datasets Wiki Query Entity-Based Query Docs DBpedia Articles Figure 1 An overview of the diverse tasks and datasets in B benchmark. So far, it is unclear how well existing trained neural models will perform for other text domains or textual retrieval tasks. Even more important, it is unclear how well different approaches, like sparse embeddings versus dense embeddings, generalize to out-of-distribution data. In this work, we present a novel robust and heterogeneous benchmark called BEIR, benchmarking IR, comprising of 18 retrieval datasets for comparison and evaluation of model generalization. Prior retrieval benchmarks, 1950, have issues of a comparatively narrow evaluation focusing either only on a single task, like question answering, or on a certain domain. In BEIR, we focus on diversity. We include 9 different retrieval tasks: fact-checking, citation prediction, duplicate question retrieval, argument retrieval, news retrieval, question answering, tweet retrieval, biomedical IR, and entity retrieval. Further, we include datasets from diverse text domains, datasets that cover broad topics, like Wikipedia, and specialized topics, like COVID-19 publications, different text types, news articles versus tweets, datasets of various sizes, 3.6K, 15M documents, and datasets with different query lengths, average query length between 3 and 192 words, and document lengths, average document length between 11 and 635 words. We use BEIR to evaluate 10 diverse retrieval methods from 5 broad architectures: lexical, sparse, dense, late interaction, and re-ranking. From our analysis, we find that no single approach consistently outperforms other approaches on all datasets. Further, we notice that the in-domain performance of a model does not correlate well with its generalization capabilities. Models fine-tuned with identical training data might generalize differently. In terms of efficiency, we find a trade-off between the performances and the computational cost. Computationally expensive models, like re-ranking models and late interaction model, perform the best. More efficient approaches, for example based on dense or sparse embeddings, can substantially underperform traditional lexical models like BEM25. Overall, BEM25 remains a strong baseline for zero-shot text retrieval. Finally, we notice that there can be a strong lexical bias present in datasets included within the benchmark, likely as lexical models are predominantly used during the annotation or creation of datasets. This can give an unfair disadvantage to non-lexical approaches. We analyze this for the Trick COVID-65 dataset. We manually annotate the missing relevance judgments for the tested systems and see a significant performance improvement for non-lexical approaches. Hence, future work requires better unbiased datasets that allow a fair comparison for all types of retrieval systems. With BEIR, we take an important step towards a single and unified benchmark to evaluate the zero-shot capabilities of retrieval systems. It allows to study when and why certain approaches perform well, and hopefully steers innovation to more robust retrieval systems. we release B and an integration of diverse retrieval systems and datasets in a well-documented, easy-to-use and extensible open-source package. B is model-agnostic, welcomes methods of all kinds, and also allows easy integration of new tasks and datasets. More details are available at https://github.com/ukplab/b. To related work and background to our knowledge, B is the first broad, zero-shot information retrieval benchmark. Existing works, 1950, do not evaluate retrieval in a zero-shot setting in depth. They either focus over a single task, small corpora, or on a certain domain. This setting hinders for investigation of model generalization across diverse set of domains and task types. Multi-ACAR, 19, consists of 8 question answering, QA, datasets and evaluates sentence-level answer retrieval given a question. It only tests a single task and 5 out of 8 datasets are from Wikipedia. Further, Multi-ACAR evaluates retrieval over rather small corpora. 6 out of 8 tasks have less than 100k candidate sentences, which benefits dense retrieval over lexical as previously shown. 54. KILT, 50, consists of 5 knowledge-intensive 2 tasks including a total of 11 datasets. The tasks involve retrieval, but it is not the primary task. Further, KILT retrieves documents only from Wikipedia. 2.1 Neural retrieval. Information retrieval is the process of searching and returning relevant documents for a query from a collection. In our paper, we focus on text retrieval and use document as a cover term for text of any length in the given collection and query for the user input, which can be of any length as well. Traditionally, lexical approaches like TF-IDF and BM25-55 have dominated textual information retrieval. Recently, there is a strong interest in using neural networks to improve or replace these lexical approaches. In this section, we highlight a few neural-based approaches and we refer the reader to Linnet al. 37, for a recent survey in neural retrieval. Retriever-based lexical approaches suffer from the lexical gap. 5. To overcome this, earlier techniques proposed to improve lexical retrieval systems with neural networks. Sparse methods such as doct5 query, 48, identified document expansion terms using a sequence-to-sequence model that generated possible queries for which the given document would be relevant. DeepCT, 11, on the other hand used a BERT, 13, model to learn relevant term weights in a document and generated a pseudo-document representation. Both methods still rely on BM25 for the remaining parts. Similarly, Sparta, 79, learned token-level contextualized representations with BERT and converted the document into an efficient inverse index. More recently, dense retrieval approaches were proposed. They are capable of capturing semantic matches and try to overcome the potential lexical gap. Dense retrievers map queries and documents in a shared, dense vector space. 18. This allowed the document representation to be pre-computed and indexed. A bi-encoder neural architecture based on pre-trained transformers has shown strong performance for various open domain question answering tasks. 19, 31, 35, 43. This dense approach was recently extended by hybrid lexical dense approaches which aims to combine the strengths of both approaches. 17, 57, 42. Another parallel line of work proposed an unsupervised domain adaptation approach, 35, 43, for training dense retrievers by generating synthetic queries on a target domain. Lastly, Colbert, 32, contextualized late interaction over BERT, computes multiple contextualized embeddings on a token level for queries and documents and uses an maximum similarity function for retrieving relevant documents. Re-ranking-based neural re-ranking approaches use the output of a first-stage retrieval system, often BM25, and re-ranks the documents to create a better comparison of the retrieved documents. Significant improvement in performance was achieved with the cross-attention mechanism of BERT, 46. However, at a disadvantage of a high computational overhead, 53. 3. The BEIR benchmark BEIR aims to provide a one-stop zero-shot evaluation benchmark for all diverse retrieval tasks. To construct a comprehensive evaluation benchmark, the selection methodology is crucial to collect tasks and datasets with desired properties. For BEIR, the methodology is motivated by the following three factors. Diverse tasks. Information retrieval is a versatile task and the lengths of queries and indexed documents can differ between tasks. Sometimes, queries are short, like a keyword, while in other cases, they can be long like a news article. Similarly, indexed documents can sometimes be long, and for other tasks, short like a tweet. 2. Diverse domains. Retrieval systems should be evaluated in various types of domains. From broad ones like news or Wikipedia, to highly specialized ones such as scientific publications in one particular field. Hence, we include domains which provide a representation of real-world problems and are diverse, ranging from generic to specialized. 3. Task difficulties. Our benchmark is challenging and the difficulty of a task included has to be sufficient. If a task is easily solved by any algorithm, it will not be useful to compare various models used for evaluation. We evaluated several tasks based on existing literature and selected popular tasks which we believe are recently developed, challenging and are not yet fully solved with existing approaches. 4. Diverse annotation strategies. Creating retrieval datasets are inherently complex and are subject to annotation biases. See Section 6 for details, which hinders a fair comparison of approaches. To reduce the impact of such biases, we selected datasets which have been created in many different ways. Some were annotated by crowd workers, others by experts, and others are based on the feedback from large online communities. In total, we include 18 English zero-shot evaluation datasets from 9 heterogeneous retrieval tasks. As the majority of the evaluated approaches are trained on the MS Marco 45 dataset, we also report performances on this dataset, but don't include the outcome in our zero-shot comparison. We would like to refer the reader to Appendix D where we motivate each one of the 9 retrieval tasks and 18-3 split. Train dev title relevancy #pairs #query #corpus average. D/Q query MS Marco 45 7 binary 532,761 6,988,841,823 1.15.96 55.98 Biomedical trick COVID 65 NF corpus 7 BioASQ 61 3333 level 3 level binary 110,575 32,916 324 5,323 500 171,332 3,633 14,914,602 493.5 38.24.7 10.603.308.05 160.77 232.26 202.61 Question answering QA Wikipedia Finance NQ 34 Hotpot QA 76 FIQA 2018, 44, 337 binary 132,803 170,000 14,166, 5,447 500, 3,452 7,405 648. 2,681,468 5,233,329 57,638 1.22.02.69.16 17.61 10.77 78.88 46.30 132.32 Tweet Retrieval Twitter Signal 1M, RT, 59, 73 Level, 97 2,866,316 19.69.30 13.93 News Retrieval News Truck News, 58, Robust 04, 64, 375 Level 3 Level, 57 249 594,977 528,155 19.6 69.9 11.14 15.27 634.79 466.40 Argument Retrieval MISC Argu Anna, 67, Tush 2020, 6, 33 Binary 3 Level, 1,406 49 8,674 382,545 1.0 19.0 192.986.55 166.80 292.37 Duplicate Question Retrieval Stack X Quora Cadup Stack, 25, Quora 37 Binary 5,000 13,145 10,457,199 522,931 1.4 1.68.5 99.53 129.09 11.44 Entity Retrieval Wikipedia DBpedia, 21, 33 Level, 67 404,635,922 38.25.39 49.68 Citation Prediction Scientific Syntax, 9, 3 Binary, 1,025,657 4.99.38 176.19 Fact-checking Wikipedia Scientific Fever, 60, Climate Fever, 14, SCI Fact, 68, 333 Binary 140,085, 926,666, 6,666 1,535 305 416,568 5,416,593 5,183 1.23.0 1.18.13 20.13 12.37 84.76 84.76 213.63 Task, Domain, Dataset, Passage Retrieval MISC Biomedical Information Retrieval IR, Test Average Word Lengths Document Table 1, Statistics of Datasets in B Benchmark. Few datasets contain documents without titles. Relevancy indicates the query document relation, binary, relevant, non-relevant, or graded into sublevels. Average D/Q indicates the average relevant documents per query. Datasets in depth. Examples for each dataset are listed in Table 8. We additionally provide dataset licenses in Appendix E, and links to the datasets in Table 5. Table 1 summarizes the statistics of the datasets provided in B. A majority of datasets contain binary relevancy judgments, i.e. relevant or non-relevant, and a few contain fine-grained relevancy judgments. Some datasets contain few relevant documents for a query, too, while other datasets like TRIC-COVID-65 can contain up to even 500 relevant documents for a query. Only 8 out of 19 datasets, including MS Marco, have training data denoting the practical importance for zero-shot retrieval benchmarking. All datasets except Argu-ANA 67 have short queries, either a single sentence or 2 to 3 keywords. Figure 1 shows an overview of the tasks and datasets in the B benchmark. Information retrieval, IR, is ubiquitous. There are lots of datasets available within each task and further even more tasks with retrieval. However, it is not feasible to include all datasets within the benchmark for evaluation. We tried to cover a balanced mixture of a wide range of tasks and datasets and paid importance not to overweight a specific task like question answering. Future datasets can easily be integrated in B, and existing models can be evaluated on any new dataset quickly. The B website will host an actively maintained leaderboard too with all datasets and models. 3.1 Dataset and diversity analysis. The datasets present in B are selected from diverse domains ranging from Wikipedia, scientific publications, Twitter, news, to online user communities, and many more. To measure the diversity in domains, we compute the domain overlap between the pairwise datasets using a pairwise weighted Jacquard similarity, 26, score on unigram word overlap between all dataset pairs. For more details on the theoretical formulation of the similarity score, please refer to Appendix F. Figure 2 shows a heat map denoting the pairwise weighted Jacquard scores and the clustered force-directed placement diagram. Nodes, or datasets, close in this graph have a high word overlap, while nodes far away in the graph have a low overlap. From Figure 2, we observe a rather low weighted Jacquard word overlap across different domains, indicating that B is a challenging benchmark where approaches must generalize well to diverse out-of-distribution domains. 3.2 B Software and Framework. The B Software 3 provides an easy-to-use Python framework, pip install B, for model evaluation. It contains extensive wrappers to replicate experiments and evaluate models from well-known repositories including Sentence Transformers, 53, Transformers, 72, Answerini, 74, DPR, 31, Elasticsearch, Colbert, 32, and Universal Sentence Encoder, 75. This makes the software useful for both academia and industry. The software also provides you with all IR-based metrics from precision, recall, map, mean average precision, MR, mean reciprocal rate, to NDCG23B leaderboard, https://tinil.com/b-leaderboard B code and documentation, https://github.com/ukplab/b4 TRIC-COVID 0.8 BIOSQ 0.51 NF Corpus 0.39 0.44 NQ 0.24 0.22 0.19 0.7 Hotpot QA 0.16 0.16 0.13 0.46 Signal 1M, RT, 0.14, 0.13, 0.11, 0.34, 0.25, 0.6 FIQA 2018 0.18, 0.17, 0.15, 0.28, 0.17, 0.26 Arguana 0.21, 0.19, 0.17, 0.34, 0.22, 0.26, 0.33 Tush 2020 0.20, 0.19, 0.17, 0.36, 0.21, 0.29, 0.41, 0.44, 0.5 Kadupstack 0.18, 0.18, 0.14, 0.24, 0.16, 0.20, 0.30, 0.22, 0.29 Quora 0.18, 0.17, 0.15, 0.33, 0.22, 0.30, 0.36, 0.29, 0.37, 0.29, 0.4 dBpedia 0.16, 0.15, 0.13, 0.44, 0.89, 0.24, 0.17, 0.21, 0.20, 0.15, 0.22 Sidix 0.32, 0.29, 0.23, 0.26, 0.16, 0.16, 0.22, 0.24, 0.23, 0.26, 0.22, 0.16 Fever 0.18, 0.18, 0.15, 0.52, 0.8, 0.27, 0.20, 0.24, 0.24, 0.18, 0.25, 0.78, 0.19, 0.3 SCI Fact 0.44, 0.53, 0.41, 0.19, 0.13, 0.11, 0.15, 0.18, 0.17, 0.16, 0.15, 0.13, 0.26, 0.15 Truck News 0.18, 0.16, 0.15, 0.42, 0.29, 0.40, 0.32 0.34, 0.37, 0.23, 0.32, 0.28, 0.20, 0.32, 0.14, 0.2 Robust 04 Truck News Fever SCI Fact Sidix Quora dBpedia Kadupstack Arguana Tush 2020 FIQA 2018 Signal 1M RT, NQ Hotpot QA Bio ASQNF Corpus Trick COVID Robust 040.23 0.21 0.18 0.46 0.31 0.34 0.35 0.38 0.35 0.23 0.31 0.30 0.24 0.35 0.18 0.45 Figure 2, domain overlap across each pairwise dataset in the B benchmark. Heat map, left, shows the pairwise weighted Jacquard similarity scores between B datasets. 2D representation, right, using a 4C directed placement algorithm with network X, 20. We color and mark datasets differently for different domains. Normalized cumulative discount gain, for any top K hits. One can use the B benchmark for evaluating existing models on new retrieval datasets and for evaluating new models on the included datasets. Datasets are often scattered online and are provided in various file formats, making the evaluation of models on various datasets difficult. B introduces a standard format, corpus, queries and crawls, and converts existing datasets in this easy universal data format, allowing to evaluate faster on an increasing number of datasets. 3.3 Evaluation metric. Depending upon the nature and requirements of real-world applications, retrieval tasks can be either be precision or recall focused. To obtain comparable results across models and datasets in B, we argue that it is important to leverage a single evaluation metric that can be computed comparably across all tasks. Decision support metrics such as precision and recall, which are both rank unaware, are not suitable. Binary rank-aware metrics such as MR, mean reciprocal rate, and MAP, mean average precision, fail to evaluate tasks with graded relevance judgments. We find that normalized cumulative discount gain, NDCG at K, provides a good balance suitable for both tasks involving binary and graded relevance judgments. We refer the reader to Wang et al. 71, for understanding the theoretical advantages of the metric. For our experiments, we utilize the Python interface of the official trick evaluation tool, 63, and compute NDCG at 10 for all datasets. For experimental setup, we use B to compare diverse, recent, state-of-the-art retrieval architectures with a focus on transformer-based neural approaches. We evaluate on publicly available pre-trained checkpoints, which we provide in Table 6. Due to the length limitations of transformer-based networks, we use only the first 512 word pieces within all documents in our experiments across all neural architectures. We group the models based on their architecture: I, lexical; 2, sparse; 3, dense; 4, late interaction; and V, re-ranking. Besides the included models, the B benchmark is model agnostic, and in future different model configurations can be easily incorporated within the benchmark. I, lexical retrieval, A, BM2555, is a commonly used bag-of-words retrieval function based on token matching between two high-dimensional sparse vectors with TF-IDF token weights. We use answer_INI, 36, with the default Lucene parameters, K equals 0.9 and B equals 0.4. We index the title, if available, and passage as separate fields for documents. In our leaderboard, we also tested Elasticsearch BM25 and answer_INI and RM3 expansion, but found answer_INI BM25 to perform the best. 5.2 Sparse retrieval, A, DeepCT, 11. Uses a BERT-based uncased model trained on MS Marco to learn the term weight frequencies, TF. It generates a pseudo-document with keywords multiplied with the learned term frequencies. We use the original setup of Dye and Callan, 11, in combination with BM25 with default answer_INI parameters, which we empirically found to perform better over the tuned MS Marco parameters. B. Sparta, 79, computes similarity scores between the non-contextualized query embeddings from BERT with the contextualized document embeddings. These scores can be pre-computed for a given document, which results in a 30K dimensional sparse vector. As the original implementation is not publicly available, we re-implemented the approach. We fine-tune a distill BERT, 56, model on the MS Marco dataset and use sparse vectors with 2000 non-zero entries. C. DocT5 query, 47, is a popular document expansion technique using AT5, base, 52, model trained on MS Marco to generate synthetic queries and append them to the original document for lexical search. We replicate the setup of Nogueira and Lin, 47, and generate 40 queries for each document and use BM25 with default answer_INI parameters. 3. Dense retrieval, A, DPR, 31, is a two-tower bi-encoder trained with a single BM25 hard negative and in-batch negatives. We found the open-sourced multi-model to perform better over the single NQ model in our setting. The multi-DPR model is a BERT-based uncased model trained on 4 QA datasets, including titles NQ, 34, trivia QA, 30, web questions, 4, and curate TREC, 3. B. ANS, 73, is a bi-encoder constructing hard negatives from an approximate nearest neighbor, an index of the corpus, which in parallel updates to select hard negative training instances during fine-tuning of the model. We use the publicly available Roberta, 41, model trained on MS Marco, 45, for 600 k-steps for our experiments. C. TARS-B, 23, is a bi-encoder trained with balanced topic-aware sampling using dual supervision from a cross-encoder and a call-BEIR model. The model was trained with a combination of both a pairwise margin MSE, 24, loss and an in-batch negative loss function. D. GenQ, is an unsupervised domain adaptation approach for dense retrieval models by training on synthetically generated data. First, we fine-tune a T5, base, 52, model on MS Marco for 2 epochs. Then, for a target dataset we generate 5 queries for each document using a combination of top K and nucleus sampling, top K, 25, top P, 0.95. Due to resource constraints, we cap the maximum number of target documents in each dataset to 100K. For retrieval, we continue to fine-tune the TARS-B model using in-batch negatives on the synthetic queries and document pair data. Note, GenQ creates an independent model for each task. For late interaction, a call-BEIR, 32, encodes and represents the query and passage into a bag of multiple contextualized token embeddings. The late interactions are aggregated with some of the max pooling query term and a dot product across all passage terms. We use the call-BEIR model as a dense retriever, end-to-end retrieval as defined. 32. First top K candidates are retrieved using AN with face, 29, face depth equals 100, and call-BEIR re-ranks by computing the late aggregated interactions. We train a BERT-based uncased model, with maximum sequence length of 300 on the MS Marco dataset for 300 k-steps. V. Re-ranking model, A. BM25 plus CE, 70, re-ranks the top 100 retrieved hits from a first-stage BM25, Anzarini, model. We evaluated 14 different cross-attentional re-ranking models that are publicly available on the Hugging Face Model Hub and found that a 6-layer, 384H Mini-LM, 70, cross-encoder model offers the best performance on MS Marco. The model was trained on MS Marco using a knowledge distillation setup with an ensemble of 3 teacher models, BERT-base, BERT-large, and Albert-large models following the setup in Hofstadter et al., 24. 5 results and analysis. In this section, we evaluate and analyze how retrieval models perform on the B benchmark. Table 2 reports the results of all evaluated systems on the selected benchmark datasets. As a baseline, we compare our retrieval systems against BM25. Figure 3 shows on how many datasets a respective model is able to perform better or worse than BM25. 1 in-domain performance is not a good indicator for out-of-domain generalization. We observe BM25 heavily underperforms neural approaches by 7 to 18 points on in-domain MS Marco. However, B reveals it to be a strong baseline for generalization and generally outperforming many other, more complex approaches. This stresses the point that retrieval methods must be evaluated on a broad range of datasets. 2-term weighting fails. Document expansion captures out-of-domain keyword vocabulary. DeepCT and Sparta both use a transformer network to learn term weighting. While both methods 6 model, lexical late interaction re-ranking dataset, BM25 Deep CT Sparta Doc T5 Query DPR and Stars B Gen Q Call Bear BM25 plus CEMS Marco 0.228.0.3380.4080.4080.4010.4010.4013 Trick COVID Bio ASQNF Corpus 0.3050.523.0.350 NQ Hotpot QAFI QA 2018 0.329 0.2950.446 0.330.584.307.0.523.0.524.307.0.317 Signal 1M RT 0.300.269.0.252.0.307.0.155.0.289.0.274.0.338 Trick News Robust 0.390.396.0.393.0.427.0.391.0.431.0.475 Argu Anatosh 2020 0.310.309.0.156.0.279.0.175 0.1310415.0.240.0.429.0.162.0.233.0.20330.211.0.271 Cadup Stack Quora 0.296.0.296.0.294.830.350.350.350.354.0.854.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540.370.82540 0.05 dBpedia 0.313 0.177 0.314 0.331 0.263 0.281 0.384 0.328 0.392 0.409 Sedex 0.158 0.124 0.126 0.162 0.077 0.122 0.149 0.143 0.145 0.166 Fever Climate Fever SCI Fact 0.753 0.213 0.665 0.353 0.066 0.630 0.596 0.082 0.582 0.714 0.201 0.675 0.562 0.148 0.318 0.669 0.198 0.507 0.700 0.228 0.643 0.669 0.175 0.644 0.771 0.184 0.671 0.819 0.253 0.688 Average Performance versus BM25 27.9%, 20.3% plus 1.6%, 47.7%, 7.4%, 2.8%, 3.6% plus 2.5% plus 11% Sparse dense Table 2, in-domain and zero-shot performances on B benchmark. All scores denote NDCG at 10. The best score on a given dataset is marked in bold, and the second best is underlined. Corresponding recall at 100 performances can be found in Table 9. Indicates the in-domain performances. Perform well in-domain on MS Marco, they completely fail to generalize well by underperforming BM25 on nearly all datasets. In contrast, document expansion-based doc-T5 query is able to add new relevant keywords to a document and performs strong on the B datasets. It outperforms BM25 on 11/18 datasets while providing a competitive performance on the remaining datasets. 3 dense retrieval models with issues for out-of-distribution data. Dense retrieval models, ESP. ANTS and TARSB, that map queries and documents independently to vector spaces, perform strongly on certain datasets, while on many other datasets perform significantly worse than BM25. For example, dense retrievers are observed to underperform on datasets with a large domain shift compared from what they have been trained on, like in BioASQ, or task shifts like in TUSH 2020. DPR, the only non-MS Marco trained dataset overall performs the worst in generalization on the benchmark. 4 re-ranking and late interaction models generalize well to out-of-distribution data. The cross-attentional re-ranking model, BM25 plus CE, performs the best and is able to outperform BM25 on almost all, 16/18, datasets. It only fails on Arguana and TUSH 2020, 2 retrieval tasks that are extremely different to the MS Marco training dataset. The late interaction model call BEIR computes token embeddings independently for the query and document, and scores query, document, pairs by a cross-attentional like MaxSim operation. It performs a bit weaker than the cross-attentional re-ranking model, but is still able to outperform BM25 on 9/18 datasets. It appears that cross-attention and cross-attentional-like operations are important for a good out-of-distribution generalization. 5 strong training losses for dense retrieval leads to better out-of-distribution performances. TARS-B provides the best zero-shot generalization performance among its dense counterparts. It outperforms ANTS on 14/18 and DPR on 17/18 datasets respectively. We speculate that the reason lies in a strong training setup in combination of both in-domain batch negatives and margin MSE losses for the TARS-B model. This training loss function, with strong ensemble teachers in a knowledge distillation setup, shows strong generalization performances. 6. TARS-B model prefers to retrieve documents with shorter lengths. TARS-B underperforms ANTS on 2 datasets, TRICOVID by 17.3 points and TUSH 2020 by 7.8 points. We observed that these models retrieve documents with vastly different lengths as shown in Figure 4. On TRICOVID, TARS-B retrieves documents with a median length of mere 10 words versus ANTS with 160 words. Similarly on TUSH 2020, 14 words versus 89 words with TARS-B and ANTS respectively. As discussed in Appendix H, this preference for shorter or longer documents is due to the used loss function. 7. 2016 10 BM25-2-10-20 BM25 plus CE TRICOVID, 58, 12-69-986-10-12 Doc T5 Call BEIR TARS-B Query Gen Q TUSH 2020, 5. TARS-B ANTS 42-14-16 ANTS Sparta 10-17 DPR-18 Deep CT0 Figure 3, Comparison of zero-shot neural retrieval performances with BM25. Re-ranking-based models, i.e., BM25 plus CE and sparse model, Doc T5 query outperform BM25 on more than half the BEIR evaluation datasets. 100, 200, 300, 400, 500, 0 TARS-B ANTS 100, 200, 300, 400, 500. Figure 4. Distribution plots. 22. For top 10 retrieved document lengths, in words, using TARS-B, blue, top, or ANTS, orange, bottom. TARS-B has a preference towards shorter documents in B. 7. Does domain adaptation help improve generalization of dense retrievers? We evaluated GenQ, which further fine-tunes the TARS-B model on synthetic query data. It outperforms the TARS-B model on specialized domains like scientific publications, finance or Stack Exchange. On broader and more generic domains, like Wikipedia, it performs weaker than the original TARS-B model. 5.1 Efficiency, retrieval latency and index sizes. Models need to potentially compare a single query against millions of documents at inference, hence, a high computational speed for retrieving results in real time is desired. Besides speed, index sizes are vital and are often stored entirely in memory. We randomly sample 1 million documents from DBpedia, 21, and evaluate latency. For dense models, we use exact search, while for call BEIR we follow the original setup, 32, and use approximate nearest neighbor search. Performances on CPU were measured with an 8-core Intel Xeon Platinum 8168 CPU at 2.70 GHz and on GPU using a single NVIDIA Tesla V100. CUDA 11.0. Trade-off between performance and retrieval latency. The best out-of-distribution generalization performances by re-ranking top 100 BM25 documents and with late interaction models come at the cost of high latency, 350 ms, being slowest at inference. In contrast, dense retrievers are 20-30x faster, 20 ms, compared to the re-ranking models and follow a low latency pattern. On CPU, the sparse models dominate in terms of speed, 20-25 ms. dbpedia, 21, 1 million, Retrieval Latency Index Rank Model DIM. GPU-CPU size, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. BM25 plus CE Callbear Doc T5 Query BM25 TARS B Gen Q and Sparta Deep CT DPR 128 768 768 768 2000 768 450 ms 350 ms 14 ms 14 ms 20 ms 19 ms 6100 ms 30 ms 20 ms 125 ms 125 ms 275 ms 20 ms 25 ms 230 ms 0.4 GB 20 GB 0.4 GB 0.4 GB 3 GB 3 GB 3 GB 12 GB 0.4 GB 3 GB Trade-off between performance and index sizes. Lexical, re-ranking and dense methods have the small table 3, estimated average retrieval latency and dist index sizes, 3 GB, to store 1M documents. From index sizes for a single query in dbpedia, 21. dbpedia. Sparta requires the second largest index ranked from best to worst on Zero-shot to store a 30K dim sparse vector, while Callbear lower the latency or memory is desired. Requires the largest index as it stores multiple 128 dim dense vectors for a single document. Index sizes are especially relevant when document sizes scale higher. Callbear requires 900 GB to store the BIOSQ, 15M documents, index, whereas BM25 only requires 18 GB. 6. Impact of annotation selection bias. Creating a perfectly unbiased evaluation dataset for retrieval is inherently complex and is subject to multiple biases induced by the annotation guidelines, 2. Annotation setup, and by the 3. Human annotators. Further, it is impossible to manually annotate the relevance for all query document pairs. Instead, existing retrieval methods are used to get a pool of candidate documents which are then marked for their relevance. All other unseen documents are assumed to be irrelevant. This is a source for selection bias. 39. A new retrieval system might retrieve vastly different results than the system used for the annotation. These hits are automatically assumed to be irrelevant. Many B datasets are found to be subject to a lexical bias, i.e. a lexical-based retrieval system like TF-IDF or BM25 has been used to retrieve the candidates for annotation. For example, in BIOSQ, candidates have been retrieved for annotation via term matching with boosting tags. 61. Creation of signal 1M, RT, involved retrieving tweets for a query with 7 out of these 8 techniques relying upon 8 model. BM25 Deep CT Sparta Doc T5 Query DPR and STARS B Callbear BM25 plus CE whole at 10, in percent. 6.4%, 19.4%, 12.4%, 2.8%, 30.6%, 14.4%, 31.8%, 12.4%, 1.6% NDCG at 10 performances before and after manual annotation on TrickCovid. 65, original, W/holes. 0.656, 0.406, 0.538, 0.713, 0.332, 0.654, 0.481, 0.677, 0.757 annotated. W/O holes. 0.668, 0.472, 0.624, 0.714, 0.445, 0.735, 0.555, 0.735, 0.760. Table 4. Whole at 10 analysis on TrickCovid. Annotated scores show improvement in performances after removing holes at 10. Documents in top 10 hits unseen by annotators, across each model. Lexical term matching signals, 59. Such a lexical bias disfavors approaches that don't rely on lexical matching, like dense retrieval methods, as retrieved hits without lexical overlap are automatically assumed to be irrelevant, even though the hits might be relevant for a query. In order to study the impact of this particular type of bias, we conducted a study on the recent TrickCovid dataset. TrickCovid used a pooling method, 38-40, to reduce the impact of the aforementioned bias. The annotation set was constructed by using the search results from the various systems participating in the challenge. Table 4 shows the whole at 10 rate, 73, for the tested systems, i.e., how many top 10 hits is each system retrieving that have not been seen by annotators. The results reveal large differences between approaches. Lexical approaches like BM25 and DocT5 query have a rather low whole at 10 value of 6.4% and 2.8%, indicating that the annotation pool contained the top hits from lexical retrieval systems. In contrast, dense retrieval systems like ANTS and TASB have a much higher whole at 10 of 14.4% and 31.8%. Indicating that a large fraction of hits found by these systems have not been judged by annotators. Next, we manually added for all systems, the missing annotation, or holes, following the original annotation guidelines. During annotation, we were unaware of the system who retrieved the missing annotation to avoid a preference bias. In total, we annotated 980 query document pairs in TrickCovid. We then recomputed NDCG at 10 for all systems with this additional annotations. As shown in Table 4, we observe that lexical approaches improves only slightly, for example for DocT5 query just from 0.713 to 0.714 after adding the missing relevance judgments. In contrast, for the dense retrieval system ANTS, the performance improves from 0.654, slightly below BM25, to 0.735, which is 6.7 points above the BM25 performance. Similar improvements are noticed in BEIR, 5.8 points. Even though many systems contributed to the TrickCovid annotation pool, the annotation pool is still biased towards lexical approaches. 7 conclusions and future work. In this work, we presented BEIR, a heterogeneous benchmark for information retrieval. We provided a broader selection of target tasks ranging from narrow expert domains to open domain datasets. We included 9 different retrieval tasks spanning 18 diverse datasets. By open sourcing BEIR, with a standardized data format and easy-to-adapt code examples for many different retrieval strategies, we taken important steps towards a unified benchmark to evaluate the zero-shot capabilities of retrieval systems. It hopefully steers innovation towards more robust retrieval systems and to new insights which retrieval architectures perform well across tasks and domains. We studied the effectiveness of 10 different retrieval models and demonstrate that in-domain performance cannot predict how well an approach will generalize in a zero-shot setup. Many approaches that outperform BM25 on an in-domain evaluation perform poorly on the BEIR datasets. Cross-attentional re-ranking, late interaction BEIR, and the document expansion technique DocT5 query performed overall well across the evaluated tasks. Our study on annotation selection bias highlights the challenge of evaluating new models on existing datasets, even though TrickCovid is based on the predictions from many systems, contributed by a diverse set of teams. We found largely different whole at 10 rates for the tested systems, negatively affecting non-lexical approaches. Better datasets that use diverse pooling strategies are needed for a fair evaluation of retrieval approaches. BEIR integrate a large number of diverse retrieval systems into BEIR, creating such diverse pools becomes significantly simplified. 9 references: 1. Amin Ahmed, Noah Constant, Yingfei Yang, and Daniel So. 2019 ReQA, an evaluation for end-to-end answer retrieval models. In proceedings of the second workshop on machine reading for question answering, pages 137146, Hong Kong, China. Association for Computational Linguistics. 18. 2. Akari Asai, Jungo Kasai, Jonathan Clark, Kenton Lee, Yoon Sol Choi, and Hanan Hajishurzi. 2021 XOR QA, Cross-Lingual Open Retrieval Question Answering. In proceedings of the 2021 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, pages 547564, online. Association for Computational Linguistics. 17. 3. Petter-Bordy and Jan Edevi. 2015 Modeling of the Question Answering Task in the Yodar-Car System. In International Conference of the Cross-Language Evaluation Forum for European Languages, pages 222228. Springer. 6. 4. Jonathan Birant, Andrew Cho, Roy Frostig, and Percy Liang. 2013 Semantic Parsing on Freebase from Question-Answer Pairs. In proceedings of the 2013 Conference on Empirical Methods in Natural Language Processing, pages 1533-1544, Seattle, Washington, USA. Association for Computational Linguistics. 6. 5. Adam Berger, Rich Keruna, David Kohn, Dane Freitag, and Vibhu Mittal. 2000 Bridging the Lexical Chasm, Statistical Approaches to Answer Finding. In proceedings of the 23rd Annual International ACM SIGA Conference on Research and Development in Information Retrieval, pages 192199. 1. 3. 6. Alexander Bondarenko, Makefrobe, Miriam Belusif, Lukas Gianap, Yarmen Adja, Alexander Panchenko, Chris Biermann, Benno Stein, Henning Wachsmuth, Martin Pottast, and Matthias Hazen. 2020 Overview of TUSH 2020, Argument Retrieval. In Working Notes Papers of the CLEF 2020 Evaluation Labs, Volume 2696 of SIR Workshop Proceedings. 4, 19, 22, 7, Vera Petiva, Demian Golipa, Artem Sokolov, and Stefan Rieseler. 2016 A Full-Text Learning to Rank Dataset for Medical Information Retrieval. In proceedings of the 38th European Conference on Information Retrieval, SIR 2016, pages 716722. 4, 18, 8, Danchi Chen, Adam Fish, Jason Weston, and Antoine Boards. 2017 Reading Wikipedia to Answer Open Domain Questions. In proceedings of the 55th Annual Meeting of the Association for Computational Linguistics, Volume 1, Long Papers, pages 1870-1879, Vancouver, Canada. Association for Computational Linguistics. 1, 18, 9, Arman Cohen, Sergey Feldman, Isabel Tagi, Doug Downey, and Daniel Weld. 2020 Spectre, Document Level Representation Learning Using Citation-Informed Transformers. In proceedings of the 58th Annual Meeting of the Association for Computational Linguistics, pages 2270-2282, online. Association for Computational Linguistics. 4. 19, 10. David Corney, Dioa Albaca, Miguel Martinez, and Samir Musa. 2016 What do a million news articles look like? In proceedings of the first international workshop on recent trends in news information retrieval co-located with 38th European Conference on Information Retrieval, ESR 2016, pages 42-47. 18, 11, Jian Dai and Jamie Callan. 2020 Context-aware term waiting for first stage passage retrieval. In proceedings of the 43rd International ACM SIGA Conference on Research and Development in Information Retrieval, SIGA 20, page 1533-1536, New York, NY, USA. Association for Computing Machinery. 3, 6, 12, Jacob Devlin, Mingwei Chang, Kenton Lee, and Christina Tautanova. 2018 BERT, Pre-training of Deep Bidirectional Transformers for Language Understanding. R14 Preprint R14 18 10.04805. 110, 13, Jacob Devlin, Mingwei Chang, Kenton Lee, and Christina Tautanova. 2019 BERT, Pre-training of Deep Bidirectional Transformers for Language Understanding. In proceedings of the 2019 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, Volume 1, Long and Short Papers, pages 4171-4186, Minneapolis, Minnesota. Association for Computational Linguistics. 3, 14, Thomas Digelman, Jordan Boyd Grabber, Janice Bullion, Massimiliano Ciaramita, and Marcus Leopold. 2020 Climate Fever, a dataset for verification of real-world climate claims. 4, 2015, Yingqi Question Yuqin Ding, Xinglu, Kailu, Ruiyang Ren, Xinjiao, Daxiang Dong, Huawu, and Haifeng Wang. 2020 Rocket QA, an optimized training approach to dense passage retrieval for open domain question answering. 1, 17, 16, Anlei Dong, Ruicheng Zhang, Pranam Kolari, Xingbai, Fernando Diaz, Yi Chang, Jiaohui Zheng, and Hongguan Zhou. 2010 Time is of the essence, improving recency ranking using Twitter data. In proceedings of the 19th International Conference on World Wide Web, WWW10, page 331340, New York, NY, USA. Association for Computing Machinery. 17, 17, Lu Yugao, Qian Dai, Tongfei Chen, Jun Fan, Benjamin Van Derm, and Jamie Callan. 2020 Complementing Lexical Retrieval with Semantic Residual Embedding. 3, 17, 18, Daniel Jilic, Alessandro Presta, and Gaurav Singh Tamar. 2018 End-to-End Retrieval in Continuous Space. 3, 19, Mandigyo, Yinfei Yang, Daniel So, Qinlan Shen, and Noah Constant. 2020 Multi-ACAR, a cross-domain evaluation for retrieval question-answering models. 2, 3, 20, Arika Hagberg, Daniela Skult, and Pieter J. Swart. 2008 Exploring Network Structure, Dynamics, and Function using NetworkX. In proceedings of the 7th Python in Science Conference, pages 11-15, Pasadena, CAUSA. 5, 21, Fia Hasabi, Fedor Nikolaev, Chnyan Zirang, Christian Belog, Svein Erik Bratsberg, Alexander Kotov, and Jamie Callan. 2017 BEIR Entity V2, a test collection for entity search. In proceedings of the 40th International ACM SIGA Conference on Research and Development in Information Retrieval, SIGA 17, pages 1265–1268. ACM 4, 8, 19, 22, Jerry L. Hintz and Ray D. Nelson. 1998 Violin Plots, a box plot density trace synergism. The American Statistician, 52, 2181-184. 8, 24, 23, Sebastian Hofstadter, Xingqie Lin, Zhenghong Yang, Jimmy Lin, and Alan Hanbury. 2021 Efficiently Teaching an Effective Dense Retriever with Balanced Topic-Aware Sampling. In Proc. of SIGA. 6, 24, Sebastian Hofstadter, Sophia Altimer, Michael Schroeder, Meet Sirkan, and Alan Hanbury. 2021 Improving Efficient Neural Ranking Models with Cross-Architecture Knowledge Distillation. 6, 21, 25, Doris Hoogveen, Karen M. Vesper, and Timothy Baldwin. 2015 CADUP-STAC, a benchmark data set for community question answering research. In proceedings of the 20th Australasian Document Computing Symposium, pages 18. 4, 19, 26, Sergey Iyev. 2010 Improved Consistent Sampling, Weighted Minhash and L1 Sketching. In 2010 IEEE International Conference on Data Mining, pages 246–255. IEEE 4, 20, 27, Mingji, Yuju Sun, Marina Danilevsky, Jia Han, and Jingao. 2010 Graph Regularized Transductive Classification on Heterogeneous Information Networks. In Machine Learning and Knowledge Discovery in Databases, pages 575–86, Berlin, Heidelberg. Springer Berlin Heidelberg. 19, 28, Jingjiang and Chengxiangjai. 2007 An Empirical Study of Tokenization Strategies for Biomedical Information Retrieval. Information Retrieval, 10, 4–5341363. 1811, 29, Jeff Johnson, Mathij Staus, and Herv Jegger. 2017 Billion Scale Similarity Search with GPUs. R14 Preprint R14 1702.08734. 6, 30, Manda Joshi, Yoon-Sol Choi, Daniel Weld, and Luke Zettel-Moyer. 2017 Trivia QA, a large-scale distantly supervised challenge dataset for reading comprehension. In proceedings of the 55th Annual Meeting of the Association for Computational Linguistics, Volume 1, Long Papers, pages 1601–1611, Vancouver, Canada. Association for Computational Linguistics. 6, 31, Vladimir Karpukhin, Bala Sagars, Swan Min, Patrick Lewis, Lidl Wu, Sergey Edunov, Danchi Chen, and Wento Yi. 2020 Dense Passage Retrieval for Open Domain Question Answering. In proceedings of the 2020 Conference on Empirical Methods in Natural Language Processing, EMLP, pages 6769–6781, online. Association for Computational Linguistics. 1, 3, 4, 6, 32, Omar Kottab and Matia Zaharia. 2020 Colbert, Efficient and Effective Passage Search via Contextualized Late Interaction over BERT. In proceedings of the 43rd International ACM SIGA Conference on Research and Development in Information Retrieval, SIGA 20, page 3948, New York, NY, USA. Association for Computing Machinery. 3, 4, 6, 8, 33, John M. Kleinberg. 1999 Authoritative sources in a hyperlinked environment. JACM, 46, 560462. 17, 34, Tom Kwiatkowski, Jenny Maria Palomaki, Olivia Redfield, Michael Collins, Ankur Parikh, Chris Alberti, Danielle Epstein, Ilya Polosukhin, Matthew Kelsey, Jacob Devlin, Kenton Lee, Christina N. Tautanova, Leon Jones, Mingwei Chang, Andrew Dai, Jacob Uskariot, Kwiklo, and Slav Petrov. 2019 Natural Questions, a benchmark for question answering research. Transactions of the Association of Computational Linguistics. 1, 4, 6, 18, 35, Davis Liang, Pengzhu, Siamak Shakari, Cicero Nogueira dos Santos, Ramesh Nilapati, Chaiheng Huang, and Bing Zhuang. 2020 Embedding-based zero-shot retrieval through query generation. 3, 36, Jimmy Lin, Matt Crane, Andrew Trotman, Jamie Callan, Ishan Chattopadhyaya, John Foley, Grant Ingersoll, Craig MacDonald, and Sebastiano Vina. 2016 Toward Reproducible Baselines, the Open Source IR Reproducibility Challenge. In European Conference on Information Retrieval, pages 408-420. Springer. 5, 37, Jimmy Lin, Rodrigo Nogueira, and Andrew Yates. 2020 Pre-trained Transformers for Text Ranking, BERT and Beyond. 1, 3, 38, Aldo Lipani. 2016 Fairness in Information Retrieval. In proceedings of the 39th International ACM SIGA Conference on Research and Development in Information Retrieval, SIGA 16, page 1171, New York, NY, USA. Association for Computing Machinery. 9, 39, Aldo Lipani. 2019 On Biases in Information Retrieval Models and Evaluation. PhD thesis, Technische Universität Wien. 8, 40, Aldo Lipani, Mihai Lupu, and Alan Hanbury. 2016 The Curious Incidence of Bias Corrections in the Pool. In European Conference on Information Retrieval, pages 267-279. Springer. 9, 41, Yinhan Liu, Milo Tt, Naaman Goyal, Jingfei Du, Manda Joshi, Danchi Chen, Omar Levi, Mike Lewis, Luke Zettelmoyer, and Veselin Stoyanov. 2019 Roberta, a robustly optimized BERT pre-training approach. 6, 42, Yiluan, Jacob Eisenstein, Christina Tautanova, and Michael Collins. 2021 Sparse, dense, and attentional representations for text retrieval. 3, 43, Chima, Ivan Korokov, Yinfei Yang, Keith Hall, and Ryan McDonald. 2021 Zero-shot neural passage retrieval via domain-targeted synthetic question generation. 3, 44, Macedo Meyer, Siegfried Hancha, Andre Freitas, Brian Davis, Ross McDermott, Maynel Zaralk, and Alexandra Balaa. 2018 WWW18 Open Challenge, Financial Opinion Mining and Question Answering. In companion proceedings of the Web Conference 2018, WWW18, page 1941-1942, Republic and Canton of Geneva, J. International World Wide Web Conferences Steering Committee. 4, 1812, 45, Tri Nguyen, Mir Rosenberg, Xia Song, Xianfeng Gao, Srab Tiwari, Rangan Majumdar, and Li Deng. 2016 MS Marco, a human-generated machine reading C comprehension dataset. Choice, 2640:660. 1, 3, 4, 6, 17, 46, Rodrigo Nogueira and Kiangi Ancho. 2020 passage re-ranking with BERT. R14 preprint R14 1901.04085. 1, 3, 17, 47, Rodrigo Nogueira, Jimmy Lin, and AI Epistemic. 2019 from Doc2 Query to Doctquery. Online preprint. 6, 48, Rodrigo Nogueira, Wei Yang, Jimmy Lin, and Kiangi Ancho. 2019 document expansion by query prediction. 3, 49, Lawrence Page, Sergey Brin, Rajiv Motwani, and Terry Winograd. 1999 The PageRank citation ranking, bringing order to the web. Technical Report 1999-66, Stanford InfoLab. Previous number equals Seidel WP 1999-0120. 17, 50, Fabio Petrini, Alexandra Pictus, Angela Fan, Patrick Lewis, Majid Yazdani, Nicola Decau, James Thorne, Joaquin Schronite, Vasilis Plakaueras, Tim Rocktaskel, and Sebastian Riedel. 2020 KILT, a benchmark for knowledge-intensive language tasks. 2, 51, Philip Radlinski, Madhu Karup, and Thorsten Joachims. 2008 How does click-through data reflect retrieval quality? In Proceedings of the 17th ACM Conference on Information and Knowledge Management, SICM 08, page 4352, New York, NY, USA. Association for Computing Machinery. 1752, Colin Raffel, Noam Shazier, Adam Roberts, Catherine Lee, Sharon Narang, Michael Maitena, Yanqi Zhu, Wei Li, and Peter J. Liu. 2020 Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer. Journal of Machine Learning Research, 21, 141-67. 6, 53, Nils Reimers and Irina Gavik. 2019 Sentence BERT, Sentence Embeddings Using Siamese BERT Networks. In Proceedings of the 2019 Conference on Empirical Methods in Natural Language Processing. Association for Computational Linguistics. 3, 4, 54, Nils Reimers and Irina Gavik. 2020 The Curse of Dense Low-Dimensional Information Retrieval for Large Index Sizes. R14 preprint R14 2012.14210. 2, 55, Stephen Robertson and Hugo Zaragoza. 2009 The Probabilistic Relevance Framework, BM25 and Beyond. Foundations and Trends in Information Retrieval, 3, 4333389. 1, 3, 5, 56. Victor San, Lysandra Debut, Julian Chaumond, and Thomas Wolfe. 2020 Distill BERT, a distilled version of BERT, smaller, faster, cheaper and lighter. 6, 57, Minjun Seo, Jinhyuk Lee, Tom Kwiatkowski, Ankur Parikh, Ali Faedi, and Hanan Hajishurzi. 2019 Real-Time Open Domain Question Answering with Dense Sparse Phrase Index. In Proceedings of the 57th Annual Meeting of the Association for Computational Linguistics, pages 443441, Florence, Italy. Association for Computational Linguistics. 3, 58, Ian Saboroff, Xudong Huang, and Donna Harmon. 2019 Trick 2019 News Track Overview. In Trick 4, 18, 59, Axel Suarez, Dioa Albaca, David Corney, Miguel Martinez, and Jose Esquivel. 2018 A data collection for evaluating the retrieval of related tweets to news articles. In 40th European Conference on Information Retrieval Research, ESR 2018, Grenoble, France, March, 2018, pages 787-86. 4, 9, 18, 60, James Thorne, Andreas Vlachos, Christos Christodoulopoulos, and Arpit Mittal. 2018 Fever, a large-scale dataset for fact extraction and verification. In Proceedings of the 2018 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, Volume 1, Long Papers, pages 809819, New Orleans, Louisiana. Association for Computational Linguistics. 1, 4, 19, 2013, 61, George Satsaranis, Georgios Barlakas, Prodromos Malakaiotis, Ionis Partalas, Matthias Chunk, Michael R. Alvars, Dirk Weissenborn, Anastasia Krithera, Sergios Petrides, Dimitris Polychronopoulos, ITAL 2015. An overview of the BEIR large-scale biomedical semantic indexing and question-answering competition. BMC Bioinformatics, 16, 1138. 4, 8, 18, 62, Aaron van den Oord, Yassia Lee, and Oriol Vinyals. 2019 Representation Learning with Contrastive Predictive Coding. 21, 63, Christoph van Gisel and Martin de Rijke. 2018 PyTrack_eval, an extremely fast Python interface to Track_eval. In Saiga. ACM. 5, 64, Ellen Voorhees. 2005 Overview of the Track 2004 Robust Retrieval Track. 4, 19, 65, Ellen Voorhees, Tas Miralam, Stephen Bedrick, Dina Demna-Fishman, William R. Hirsch, Kyle Lowe, Kirk Roberts, Ian Saboroff, and Lucy Lu Wang. 2021 Track COVID, Constructing a Pandemic Information Retrieval Test Collection. Saiga Forum, 54, 1. 2, 4, 9, 18, 66, Henning Wach-Smuth, Martin Pottast, Khalid Al-Khatib, Yamen Ajja, Jonna Pustman, Gianni Question, Jonas Dush, Viral Morari, Yannick Bevendorf, and Benno Stein. 2017 Building an Argument Search Engine for the Web. In 4th Workshop on Argument Mining, ArgMining 2017, at EMLP, pages 49-59. Association for Computational Linguistics. 1967, Henning Wach-Smuth, Shahbaz Syed, and Benno Stein. 2018 Retrieval of the best counter-argument without prior topic knowledge. In Proceedings of the 56th Annual Meeting of the Association for Computational Linguistics, Volume 1, Long Papers, pages 241-251. Association for Computational Linguistics. 4, 19, 68, David Wadden, Shan-Chuan Lin, Kyle Lowe, Lucy Lu Wang, Madeleine Van Zuylen, Arman Cohen, and Hanan Hajishurzi. 2020 Fact or Fiction, Verifying Scientific Claims. In Proceedings of the 2020 Conference on Empirical Methods in Natural Language Processing, EMLP, pages 7534-7550, online. Association for Computational Linguistics. 4, 20, 69, Lucy Lu Wang, Kyle Lowe, Yoganand Chandrasekhar, Russell Riaz, Jian Yang, Doug Burdick, Darinide, Catherine Funk, Yanis Katsi, Rodney Kinney, Yuyun Yao Li, Ziyang Lu, William Merrill, Paul Mooney, Dewey Murdoch, Devvat Rishi, Cherry Sheehan, Chihongshan, Brandon Stilson, Alex Wade, Kuan San Wang, Nancy Shin Ru Wang, Chris Wilhelm, Boyazai, Douglas Raymond, Daniel S. Weld, Oren Etzioni, and Sebastian Kohlmeier. 2020 Cord-19, the COVID-19 Open Research Dataset. 1870, Wenhui Wang, Fu Wei, Li Dong, Hangbo Bao, Nan Yang, and Mingzhu. 2020 Mini-LM, Deep Self-Attention Distillation for Task-Agnostic Compression of Pre-trained Transformers. In Advances in Neural Information Processing Systems, Volume 33, pages 5776–5788. Curran Associates, Inc. 6, 71, Yining Wang, Liwei Wang, Yuanjai Li, Di He, Wei Chen, and Taiyang Lu. 2013 A Theoretical Analysis of NDCG Ranking Measures. In Proceedings of the 26th Annual Conference on Learning Theory, Cold 2013, Volume 8, page 6. 5, 72, Thomas Wolfe, Lysandra Debut, Victor San, Julian Chaumond, Clement Delange, Anthony Moi, Pierrick Sistark, Tim Raoult, Remy Louf, Morgan Funtoich, Joe Davison, Sam Schleifer, Patrick von Platen, Clara Ma, Joaquin Schroneit, Julian Plu, Can Wenzu, Tivan Lascaux, Sylvain Guga, Marima Dram, Quinton Huest, and Alexander M. Rush. 2020 Transformers, State-of-the-Art Natural Language Processing. In Proceedings of the 2020 Conference on Empirical Methods in Natural Language Processing, System Demonstrations, pages 38–45, online. Association for Computational Linguistics. 4, 73, Li Zirong, Chnyan Zirong, Yu Li, Quickfeng Tang, Xiaolin Lu, Paul Bennett, Junaid Ahmed, and Arnold Overwijck. 2020 Approximate Nearest Neighbor Negative Contrastive Learning for Dense Text Retrieval. 6, 9, 74, Palin Yang, Hui Fang, and Jimmy Lin. 2017 Anzarini, Enabling the Use of Lucene for Information Retrieval Research. In Proceedings of the 40th International ACM SIGA Conference on Research and Development in Information Retrieval, SIGA 17, page 1253–1256, New York, NY, USA. Association for Computing Machinery. 414, 75, Yinfei Yang, Daniel So, Armin Ahmed, Mandigio, Jacques Law, Noah Constant, Gustavo Hernandez Abrego, Steve Yuan, Chris Ta, Yoon Seun Sung, et al. 2020. Multilingual Universal Sentence Encoder for Semantic Retrieval. In Proceedings of the 58th Annual Meeting of the Association for Computational Linguistics, System Demonstrations, pages 87–94. 4, 76, Jilin Yang, Peng Qi, Saizheng Zhang, Yoshua Bengio, William Cohen, Ruslan Salakhat-Dinov, and Christopher D. Manning. 2018 Hotpot QA, a dataset for diverse, explainable multi-hop question answering. In Proceedings of the 2018 Conference on Empirical Methods in Natural Language Processing, pages 2369–2380, Brussels, Belgium. Association for Computational Linguistics. 4, 18, 77, Zinayu Zhang, Xiuguang Ma, Peng Shi, and Jimmy Lin. 2021 Mr. Tai Di, a multilingual benchmark for dense retrieval. 17, 78, Yiyun Zhang, David Lo, Xinxia, and Jianling Sunday 2015. Multifactor duplicate question detection in Stack Overflow. Journal of Computer Science and Technology, 30, 5981997. 1, 79, Tiancheng Zhao, Xiaopeng Liu, and Qiasong Li. 2021 Sparta, Efficient Open Domain Question Answering via Sparse Transformer Matching Retrieval. In proceedings of the 2021 Conference of the North American Chapter of the Association for Computational Linguistics, Human Language Technologies, pages 565575, online. Association for Computational Linguistics. 3, 615 Checklist 1. For all authors. A. Do the main claims made in the abstract and introduction accurately reflect the paper's contributions and scope? Yes. B. Did you describe the limitations of your work? Yes. See Appendix B. C. Did you discuss any potential negative societal impacts of your work? No. D. Have you read the ethics review guidelines and ensured that your paper conforms to them? Yes. 2. If you are including theoretical results. A. Did you state the full set of assumptions of all theoretical results? N/A. B. Did you include complete proofs of all theoretical results? N/A. 3. If you ran experiments, for example for benchmarks. A. Did you include the code, data, and instructions needed to reproduce the main experimental results, either in the supplemental material or as a URL? Yes. URL mentioned in abstract. B. Did you specify all the training details, for example, data splits, hyperparameters, how they were chosen? Yes. All results can be reproduced by the code in our repository. C. Did you report error bars, for example, with respect to the random seed after running experiments multiple times? No. We evaluate existing available pre-trained models that often come without suitable training code. Hence, in many cases, retraining the model is not feasible. D. Did you include the total amount of compute and the type of resources used, for example, type of GPUs, internal cluster, or cloud provider? No. We include the type of GPU and CPU resources we used, but not the total amount of compute that was used. For if you are using existing assets, for example, code, data, models, or curating/releasing new assets. A. If your work uses existing assets, did you cite the creators? Yes. Original papers are cited, if available. Table 5 contains the original website links for the used datasets. B. Did you mention the license of the assets? Yes. See Appendix E. C. Did you include any new assets either in the supplemental material or as a URL? Yes. No supplemental material attached to this submission. Further supplemental material can be found in our repository mentioned in the URL. D. Did you discuss whether and how consent was obtained from people whose data you're using /curating? N/A. Used datasets provide a specific dataset license, which we follow. E. Did you discuss whether the data you are using /curating contains personally identifiable information or offensive content? No. We reuse existing datasets, which most are freely available. Most datasets are from less sensitive sources, like Wikipedia or scientific publications, where don't expect personally identifiable information. Checking for offensive content in more than 50 million documents is difficult and removing it would alter the underlying dataset. 5. If you used crowdsourcing or conducted research with human subjects. A. Did you include the full text of instructions given to participants and screenshots, if applicable? N/A. We ourselves performed annotation on the TRIC-COVID dataset, where we followed the instructions from the original task website. B. Did you describe any potential participant risks, with links to Institutional Review Board, IRB, approvals, if applicable? N/O. C. Did you include the estimated hourly wage paid to participants and the total amount spent on participant compensation? N/A. Annotations were done by the authors of the paper. 16a. Complementing information. We provide the following additional sections in detail and information that complement discussions in the main paper. Limitations of the B benchmark in Appendix B. Training and in-domain evaluation task details in Appendix C. Description of all zero-shot tasks and datasets used in B in Appendix D. Details of dataset licenses in Appendix E. Overview of the weighted Jacquard similarity metric in Appendix F. Overview of the capped recall at K metric in Appendix G. Length preference for dense retrieval system in Appendix H. B. Limitations of the B benchmark. Even though we cover a wide range of tasks and domains in B, no benchmark is perfect and has its limitations. Making those explicit is a critical point in understanding the results on the benchmark and, for future work, to improve upon the benchmark. 1. Multilingual tasks. Although we aim for a diverse retrieval evaluation benchmark, due to the limited availability of multilingual retrieval datasets, all datasets covered in the B benchmark are currently English. It is worthwhile to add more multilingual datasets, 277, in consideration of the selection criteria, as a next step for the benchmark. Future work could include multi- and cross-lingual tasks and models. 2. Long document retrieval. Most of our tasks have average document lengths up to a few hundred words, roughly equivalent to a few paragraphs. Including tasks that require the retrieval of longer documents would be highly relevant. However, as transformer-based approaches often have a length limit of 512 word pieces, a fundamental different setup would be required to compare approaches. 3. Multifactor search. Until now, we focused on pure textual search in B. In many real-world applications, further signals are used to estimate the relevancy of documents, such as page rank, 49, recency, 16, authority score, 33, or user interactions such as click-through rates, 51. The integration of such signals in the tested approaches is often not straightforward and is an interesting direction for research. 4. Multi-field retrieval. Retrieval can often be performed over multiple fields. For example, for scientific publication we have the title, the abstract, the document body, the author's list, and the journal name. So far we focused only on datasets that have one or two fields. 5. Task-specific models. In our benchmark, we focus on evaluating models that are able to generalize well for a broad range of retrieval tasks. Naturally, in real world, for some few tasks or domains, specialized models are available which can easily outperform generic models as they focus and perform well on a single task. Let's say on question answering. Such task-specific models do not necessarily need to generalize across all diverse tasks. See training and in-domain evaluation. We use the MS Marco passage ranking dataset, 45, which contains 8.8 M passages and an official training set of 532,761 query passage pairs for fine-tuning for a majority of retrievers. The dataset contains queries from Bing search logs with one text passage from various web sources annotated as relevant. We find the dataset useful for training, in terms of covering a wide variety of topics and providing the highest number of training pairs. It has been extensively explored and used for fine-tuning dense retrievers in recent works, 46, 17, 15. We use the official MS Marco development set for our in-domain evaluation, which has been widely used in prior research, 46, 17, 15. It has 6,980 queries. Most of the queries have only one document judged relevant. The labels are binary. Zero-shot evaluation tasks following the selection criteria mentioned in Section 3. We include 18 evaluation datasets that span across 9 heterogeneous tasks. Each dataset mentioned below contains a document corpus denoted 17 by T and test queries for evaluation denoted by Q. We additionally provide dataset website links in Table 5 and intuitive examples in Table 8. We now describe each task and dataset included in the B benchmark below. D.1 Biomedical Information Retrieval. Biomedical information retrieval is the task of searching relevant scientific documents such as research papers or blogs for a given scientific query in the biomedical domain. 28. We consider a scientific query as input and retrieve biomedical documents as output. COVID 65 is an ad hoc search challenge based on the COVID-19 dataset containing scientific articles related to the COVID-19 pandemic. 69. We include the 16th of July 2020 version of COVID-19 dataset as corpus T and use the final cumulative judgments with query descriptions from the original task as queries QNF corpus. 7. Contains natural language queries harvested from nutrition facts, NF. We use the original splits provided alongside all content sources from NF, videos, blogs, and Q&A posts, as queries Q and annotated medical documents from PubMed as corpus T. BioASQ. 61. Task 8B is a biomedical semantic question answering challenge. We use the original train and test splits provided in Task 8B as queries Q and collect around 15 articles from PubMed provided in Task 8AM as our corpus TD.2 Open Domain Question Answering, QA. Retrieval in Open Domain Question Answering, 8, is the task of retrieving the correct answer for a question, without a predefined location for the answer. In open domain tasks, model must retrieve over an entire knowledge source, such as Wikipedia. We consider the question as input and the passage containing the answer as output. Natural questions, 34, contains Google search queries and documents with paragraphs and answer spans within Wikipedia articles. We did not use the NQ version from ReQA 1, as it focused on queries having a short answer. As a result, we parsed the HTML of the original NQ dataset and include more complex development queries that often require a longer passage as answer compared to ReQA. We filtered out queries without an answer, or having a table as an answer, or with conflicting Wikipedia pages. We retain 2,681,468 passages as our corpus T and 3,452 test queries Q from the original dataset. Hotpot QA 76 contains multi-hop-like questions which require reasoning over multiple paragraphs to find the correct answer. We include the original full wiki task setting, utilizing processed Wikipedia passages as corpus T. We held out randomly sampled 5,447 queries from training as our dev split. We use the original, paper, tasks development split as our test split QFIQA 2018, 44. Task 2 consists of opinion-based question answering. We include financial data by crawling Stack Exchange posts under the investment topic from 2009 to 2017 as our corpus T. We randomly sample out 500 and 648 queries Q from the original training split as dev and test splits. D.3 Tweet Retrieval. Twitter is a popular microblogging website on which people post real-time messages, i.e. tweets, about their opinions on a variety of topics and discuss current issues. We consider a news headline as input and retrieve relevant tweets as output. Signal 1M related tweets, 59. Task retrieves relevant tweets for a given news article title. The related tweets task provides news articles from the Signal 1M dataset, 10, which we use as queries queue. We construct our Twitter corpus T by manually scraping tweets from the provided tweet IDs in the relevancy judgments using Python package, tweepy, https://www.tweepy.org. D.4 News Retrieval Trick News, 58. 2019 track involves background linking. Given a news headline, we retrieve relevant news articles that provide important context or background information. We include the original shared task query description, single sentence, as our test queries queue and the trick Washington Post as our corpus T. For simplicity, we convert the original exponential gain relevant judgments to linear labels. 18 Robust 0464 provides a robust dataset focusing on evaluating on poorly performing topics. We include the original shared task query description, single sentence, as our test queries queue and the complete trick disks 4 and 5 documents as our corpus TD.5 argument retrieval. Argument retrieval is the task of ranking argumentative texts in a collection of focused arguments, output, in order of their relevance to a textual query, input, on different topics. Argu-ana counter-args corpus, 67, involves the task of retrieval of the best counter-argument to an argument. We include pairs of arguments and counter-arguments scraped from the online debate portal as corpus T. We consider the arguments present in the original test split as our queries queue. Tush 2020, 6. Task 1 is a conversational argument retrieval task. We use the conclusion as title and premise for arguments present in args.me, 66, as corpus T. We include the shared Tush 2020 task data as our test queries queue. The original relevance judgments, CRLs, file also included negative judgments, -2, for non-arguments present within the corpus, but for simplicity we substitute them as 0. D.6 Duplicate question retrieval. Duplicate question retrieval is the task of identifying duplicate questions asked in community question answering (CQA) forums. A given query is the input and the duplicate questions are the output. Cadupstack, 25, is a popular dataset for research in community question answering (CQA). The corpus T comprises of queries from 12 different Stack Exchange subforums: Android, English, Gaming, GIS, Mathematica, Physics, Programmers, Stats, Techs, Unix, Webmasters and WordPress. We utilize the original test split for our queries queue, and the task involves retrieving duplicate query, title and body, for an input query title. We evaluate each Stack Exchange subforum separately and report the overall mean scores for all tasks in B. Quora duplicate questions dataset identifies whether two questions are duplicates. Quora originally released containing 404,290 question pairs. We add transitive closures to the original dataset. Further, we split it into train, dev, and test sets with a ratio of about 85%, 5% and 10% of the original pairs. We remove all overlaps between the splits and ensure that a question in one split of the dataset does not appear in any other split to mitigate the transductive classification problem. 27. We achieve 522,931 unique queries as our corpus T and 5,000 dev and 10,000 test queries queue respectively. D.7 Entity retrieval. Entity retrieval involves retrieving unique Wikipedia pages to entities mentioned in the query. This is crucial for tasks involving entity linking, L. The entity-bearing query is the input and the entity abstract and title are retrieved as output. DBpedia Entity V2, 21, is an established entity retrieval dataset. It contains a set of heterogeneous entity-bearing queries Q containing named entities, IR-style keywords, and natural language queries. The task involves retrieving entities from the English part of DBpedia Corpus T from October 2015. We randomly sample out 67 queries from the test split as our dev set. D.8 Citation prediction. Citations are a key signal of relatedness between scientific papers. 9. In this task, the model attempts to retrieve cited papers, output, for a given paper title as input. Syntax. 9 contains a corpus T of 30K held out pool of scientific papers. We consider the direct citations, 1 out of 7 tasks mentioned in the original paper, as the best suited task for retrieval evaluation in B. The task includes 1K papers as queries Q with 5 relevant papers and 25, randomly selected, uncited papers for each query. D.9 Fact-checking. Fact-checking verifies a claim against a big collection of evidence, 60. The task requires knowledge about the claim and reasoning over multiple documents. We consider a sentence-level claim as input and the relevant document passage verifying the claim as output. 19 Fever, 60. The fact extraction and verification dataset is collected to facilitate the automatic fact-checking. We utilize the original paper splits as queries Q and retrieve evidences from the pre-processed Wikipedia abstracts, June 2017 dump, as our corpus T. Climate Fever, 14, is a dataset for verification of real-world climate claims. We include the original dataset claims as queries Q and retrieve evidences from the same Fever wiki corpus T. We manually included few Wikipedia articles, 25, missing from our corpus, but present within our relevance judgments. SCI Fact, 68, verifies scientific claims using evidence from the research literature containing scientific paper abstracts. We use the original publicly available dev split from the task containing 300 queries as our test queries Q, and include all documents from the original dataset as our corpus T. E-dataset licenses the authors of 4 out of the 19 datasets in the B benchmark, NF corpus, FIQA 2018, Quora, Climate Fever, do not report the dataset license in the paper or a repository. We overview the rest, MSMARCO, provided under MIT license for non-commercial research purposes. Fever, NQ, DBpedia, Signal 1M, all provided under CC BY SA 3.0 license. Trick News, Robust 04, BioASQ, data collection archives are under copyright. Arguana, Tush 2020, provided under CC BY 4.0 license. Kadupstack, provided under Apache license 2.0 license. SCI Fact, provided under the CC BY NC 2.0 license. Syntax, provided under the new General Public License version 3.0 license. Hotpot QA, provided under the CC BY SA 4.0 license. Trick COVID, provided under the Dataset License Agreement. F-Weighted Jacquard Similarity. The Weighted Jacquard Similarity J.S.T. 26, is intuitively calculated as the unique word overlap for all words present in both the datasets. More formally, the normalized frequency for an unique word K in a dataset is calculated as the frequency of word K divided over the sum of frequencies of all words in the dataset. Sk is the normalized frequency of word K in the source dataset S and Tk for the target dataset T respectively. The weighted Jacquard similarity between S and T is defined as pk-min, sk, tk, pj, s, t, equals k-max, sk, tk, where the sum is over all unique words k present in datasets S and T. GCapped recall at k score recall at k is calculated as the fraction of the relevant documents that are successfully retrieved within the top k extracted documents. More formally, the R at k score is calculated as Q1x max, RE, mathematical intersection symbol IR at k equals QI equals 1 I, where Q is the set of queries, I is the set of relevant documents for the ith query, and RE is a scored list of documents provided by the model, from which top k are extracted. However, measuring recall can be counterintuitive if a high number of relevant documents, k, are present within a dataset. For example, consider a hypothetical dataset with 500 relevant documents for a query. Retrieving all relevant documents would produce a maximum R at 100 score equals 0.2, which 20 is quite low and unintuitive. To avoid this, we cap the recall score, R_cap at k for datasets if the number of relevant documents for a query greater than k. It is defined as Q_cap at k equals 1x max, RE, mathematical intersection symbol IQI equals 1 min, k, I, where the only difference lies within the denominator, where we compute the minimum of k and I, instead of I present in the original recall. H document length preference for dense retrieval system. As we show in figure 4, TARS-B prefers retrieval of shorter documents, and in comparison, ANTS retrieves longer documents. The difference is especially extreme for the TRIC-COVID dataset. TARS-B retrieves lots of top-hit documents containing only a title and an empty abstract, while ANTS retrieves top-hit documents with a non-empty abstract. Identifying the source for this contrasting behavior is difficult, as TARS-B and ANTS use different models, Distill BERT versus RobertaBase, a different loss function, InfoNCE, 62, versus margin MSE, 24, with in-batch negatives, and different hard negative mining strategies. Hence, we decided to harmonize the training setup and to alter the training by just one aspect, the similarity function. Dense models require a similarity function to retrieve relevant documents for a given query within an embedding space. This similarity function is also used during training dense models with the InfoNCE, 62, loss, exp, to times sim, q, d plus, lq equals log pni equals 0 exp, to times sim, q, di, using n in-batch negatives for each query q and a scaling factor to, where d and denotes the relevant, positive, document for query q. Commonly used similarity functions, sim, q, d, are cosine similarity or dot product. We trained two Distill-BERT base uncased models with an identical training setup on MS Marco, identical training parameters, and only changed the similarity function from cosine similarity to dot product. As shown in Table 10, we observe significant performance differences for some B datasets. For TRIC-COVID, the dot product model achieves the biggest improvement with 15.3 points, while for a majority on other datasets, it performs worse than the cosine similarity model. We observe that these, nearly identical models retrieve documents with vastly different lengths as shown in the violin plots in Table 10. For all datasets, we find the cosine similarity model to prefer shorter documents over longer ones. This is especially severe for TRIC-COVID. A large fraction of the scientific papers, approximate 42K out of 171K, consist only of publication titles without an abstract. The cosine similarity model prefers retrieving these documents. In contrast, the dot product model primarily retrieves longer documents, i.e., publications with an abstract. Cosine similarity uses vectors of unit length, thereby having no notion of the encoded text length. In contrast, for dot product, longer documents result in vectors with higher magnitudes which can yield higher similarity scores for a query. Further, as we observe in Figure 5, relevance judgment scores are not uniformly distributed over document lengths. For some datasets, longer documents are annotated with high relevancy scores, while in others, shorter documents are. This can be either due to the annotation process, for example, the candidate selection method prefers short or long documents, or due to the task itself, where shorter or longer documents could be more relevant to the user information need. Hence, it can be more advantageous to train a model with either cosine similarity or dot product depending upon the nature and needs of the specific task. 21 Dataset website, link, MS Marco Trick COVID NF Corpus Bio ASQNQ Hotpot QAFIQA 2018 Signal 1M, RT. Trick News Robust 04 Argu Anatush 2020 Kadupstack Quorad Bedia Entity Sidex Fever Climate Fever SCI Fact https://microsoft.github.io/msmarco/https://ia.nist.gov/covid submit /index.html https://www.cl.uni-heidelberg.de/nfcorpus/statnupgroup/by/orsk.org https://re.google.com/research/natural questions https://hopotka.github.io https://sites.google.com/view/fika/https:// research.signalari.com/datasets/signal1m twitter.html https://trick.nist.gov/data/news2019.html https://trick.nist.gov/data/t13_robust.html http://argumentation.blaze.net/arguina/data https://webis.de/events/tush-20/shared-task-1.html http://www.quora.com/q/quora-data/first-quora-dataset-release-question-pairs http://github.com/deeppedia-entity/alani.org/data/fever.re http://climateefever.re https:// github.com/alani/Cefact Table 5, original dataset website, link, for all datasets present in B. Model Public Model Checkpoints, link, BM25, Anzarini, DeepCT Sparta Doc T5 Query DPR, Context, and STARS B Call Bear Mini LML6, CE. https://github.com/castorini/anzarini https://huggingface.co/bi/sentence transformers/Facebook DPRCTX_encoder multis a base https://huggingface.co/sentence transformers/Facebook-Roberta-base-ants-first https://huggingface.co/sentence transformers/Facebook-Distilbert-base-tars-b https://public.UP.2-darmstadt.the/the/cur/b//models/callbear/smarco.psg.l2.zip https://huggingface.co/cross-encoder/mini-lm-l-6-v2 table 6 publicly available model links used for evaluation in B. Relevancy 1-2 count 30 20 10 0 0 250 500 750 1000 1250 1500 relevant document lengths, in words, 1750 figure 5, annotated original relevant document lengths, in words, for TUSH 2020, 6. Majority of the relevant documents, score equals 2, on average in the original dataset are longer. Many shorter documents are annotated as less relevant, score equals 1. 22 Corpus website, link, Cord 19 Nutrition Facts PubMed Signal 1 Trick Washington Post Trick Discs 4 and 5 args.me DBpedia, 2015-10, Trick COVID, annotated, https://www.semanticcollar.org/cord19 https://nutritionfacts.org https://pubmed.nb.nlm.ni.gov https://research.signal-re.com/datasets/signal1m.html https://wiki-archive/41944/http://downloads.pedia.org/wiki-archive/4/1015/10 public.UP.2darmstadt.the/the/cur/b/datasets/trickcovid-b.zip table 7, corpus name and link used for datasets in B. Dataset query relevant document MS Marco. What fruit is native to Australia? Paragraph, Passiflora herbaceana. A rare passion fruit native to Australia. Fruits are green-skinned, white-fleshed, with an unknown edible rating. Some sources list the fruit as edible, sweet and tasty, while others list the fruits as being bitter and inedible. Aciflora herbaceana. A rare passion fruit native to Australia. Trick COVID. What is the origin of COVID-19? Title: Origin of novel coronavirus. COVID-19, a computational biology study using artificial intelligence. Paragraph: Origin of the COVID-19 virus has been intensely debated in the community. BioASQ. What is the effect of HMGB2 loss on CTCF clustering? Title: HMGB2 loss upon senescence entry disrupts genomic organization and induces CTCF clustering across cell types. Paragraph: Processes like cellular senescence are characterized by complex events giving rise to heterogeneous cell populations. However, the early molecular events driving this cascade remain elusive. NF corpus titanium dioxide and inflammatory bowel dis. Title: Titanium dioxide nanoparticles in food and personal care products. Paragraph: Titanium dioxide is a common additive in many food, personal care, and other consumer products used by people, which after use can enter the sewage system, and subsequently enter the environment as treated effluent discharged to surface waters or biosolids applied to agricultural land, or incinerated wastes. NQ. When did they stop cigarette advertising on telly? Title: Tobacco advertising. Paragraph: The first calls to restrict advertising came in 1962 from the Vision Royal College of Physicians, who highlighted the health problems and recommended stricter laws. Hotpot QA. Ellie Webster has paintings hanging in what home that serves as the residence for the mayor of New York? Title: Stokely Webster. Paragraph: Stokely Webster, 1912–2001, was best known as an American Impressionist painter who studied in Paris. His paintings can be found in the permanent collections of many museums, including the Metropolitan Museum of Art in New York, the National Museum. FIQA 2018. What is the PEG ratio? How is the PEG ratio calculated? How is the PEG ratio useful for stock investing? Paragraph: PEG is price/earnings to growth. It is calculated as price/earnings/annual EPS growth. It represents how good a stock is to buy, factoring in growth of earnings, which P/E does not. Obviously, when PEG is lower, a stock is more undervalued, which means that it is a better buy, and more likely. Signal 1M, RT, Genvoya, a gentler anti-HIV cocktail, okayed by EU regulators. Paragraph: All people with HIV should get antiretroviral drugs at WHO, by @Kgeland via @Reuters_health #AIDS #TARS Petrick News. Websites where children are prostituted are im. Title: Senate launches bill to remove immunity for websites hosting illegal content, spurred by immune from prosecution. But why? Backpage.com. Paragraph: The legislation, along with a similar bill in the House, sets the stage for a battle between Congress and some of the Internet's most powerful players, including Google and various free speech advocates, who believe that Congress shouldn't regulate web content or try to force websites to police themselves more rigorously. Robust 04. What were the causes for the Islamic Revolution relative to relations with the U.S.? Paragraph: BFN, editorial, Sow the Wind and Reap the Whirlwind. Yesterday marked the 14th anniversary of severing of diplomatic relations between the Islamic Republic and the United States of America. Several occasions arose in the last decade and a half for improving Irano-American relations. Tush 2020. Should the government allow illegal immigrants to become citizens? Title: America should support blanket amnesty for illegal immigrants. Paragraph: Undocumented workers do not receive full Social Security benefits because they are not United States citizens, nor should they be until they seek citizenship legally. Illegal immigrants are legally obligated to pay taxes. Stack command to display first few and last few lines of a file. Title, combing head and tail in a single call via pipe. Paragraph, on a regular basis, I am piping the output of some program to either head or tail. Now, suppose that I want to see the first and last 10 lines of piped output, such that I could do something like ./lot so footput head tail. Quora, how long does it take to methamphetamine out of your blood? Paragraph, how long does it take the body to get rid of methamphetamine? DBpedia, Paul Auster novels. Title, The New York Trilogy. Paragraph, The New York Trilogy is a series of novels by Paul Auster. Originally published sequentially as City of Glass, 1985, Ghosts, 1986, and The Locked Room, 1986, it has since been collected into a single volume. SIDC CFD Analysis of Convective Heat Transfer Co. Title, Application of CFD in Building Performance Simulation for the Outdoor Environment, an overview efficient on external surfaces of buildings. Paragraph. This paper provides an overview of the application of CFD in building performance simulation for the outdoor environment, focused on 4 topics. Fever Dodgeball, a True Underdog Story is an AMER. Title, Dodgeball, a True Underdog Story. Paragraph. Dodgeball, a True Underdog Story is an icon movie from 2004 American sports comedy film written and directed by Rawson Marshall Thurber and starring Vince Vaughn and Ben Stiller. The film follows friends who enter a dodgeball tournament. Climate fever. Sea level rise is now increasing faster than Title, Sea level rise. Paragraph. A sea level rise is an increase in the volume of water in the world's dict due to unexpectedly rapid ice melting oceans, resulting in an increase in global mean sea level. The rise is usually attributed to global climate change by thermal expansion of the water in the oceans and by melting of ice sheets and glaciers. Table 8. Examples of queries and relevant documents for all datasets included in B. Title, and paragraph, are used to distinguish the title separately from the paragraph within a document in the table above. These tokens were not passed to the respective models. 23 Model, Lexical Late Interaction Re-ranking Dataset, BM25 Deep CT Sparta Doc T5 Query DPR and Stars B Gen Q Call Bear BM25 plus CEMS Marco 0.6580.7520.8520.8840.8840.8650.658 Trick COVID Bio ASQNF Corpus 0.498 0.7140.250.347 0.6990.2350.409 0.3510.2430.541 0.6460.2530.212 0.2560.2080.457 0.4630.2320.387 0.5790.2800.456 0.6270.2800.464 0.6450.2540.498 0.7140.250 NQ Hotpot QAFI QA 2018 0.7600 0.7400 0.539 0.636 0.731 0.489 0.787 0.651 0.446 0.832 0.709 0. 0.5980.880, 0.5910, 0.342, 0.836, 0.578, 0.581, 0.903, 0.728, 0.593, 0.862, 0.673, 0.618, 0.912, 0.748, 0.603, 0.760, 0.740, 0.539, signal 1M, RT, 0.370, 0.299, 0.270, 0.351, 0.162, 0.239, 0.304, 0.281, 0.283, 0.370, Trick News Robust 040, 0.422, 0.375, 0.316, 0.271, 0.262, 0.215, 0.439, 0.357, 0.215, 0.211, 0.398, 0.274, 0.418, 0.331, 0.412, 0.298, 0.367, 0.310, 0.422, 0.375, Argu Anatosh 2020, 0.942, 0.538. 0.932, 0.406, 0.893, 0.381, 0.972, 0.557, 0.751, 0.301, 0.937, 0.458, 0.942, 0.431, 0.978, 0.451, 0.914, 0.439, 0.942, 0.538, Kadupstak Quora 0.606, 0.973, 0.545, 0.954, 0.521, 0.896, 0.638, 0.982, 0.403, 0.470, 0.579, 0.987, 0.622, 0.986, 0.654, 0.988, 0.624, 0.989, 0.606, 0.973, dBpedia 0.398, 0.372, 0.411, 0.365, 0.349, 0.319, 0.499, 0.431, 0.461, 0.398, Sidix 0.356, 0.314, 0.297, 0.360, 0.219, 0.269, 0.335, 0.332, 0.344, 0.356, Fever Climate Fever SCI Fact 0.931, 0.436, 0.908, 0.735, 0.232, 0.893, 0.843. 0.227, 0.863, 0.916, 0.427, 0.914, 0.840, 0.390, 0.727, 0.900, 0.445, 0.816, 0.937, 0.534, 0.891, 0.928, 0.450, 0.893, 0.934, 0.444, 0.878, 0.931, 0.436, 0.908. Sparse dense Table 9, in-domain and zero-shot retrieval performance on B datasets. Scores denote recall at 100. The best retrieval performance on a given dataset is marked in bold, and the second best performance is underlined. Indicates in-domain retrieval performance. Shows the capped recall at 100 score, Appendix G. Trick-COVID signal 1M, RT, SBIRT, method, cosine sim. Prod. 0 100 200 300 400 500 0 Trick-COVID fever SBIRT, method, cosine sim. Prod. 5 10 15 20 25 signal 1M, RT, SBIRT, method, cosine sim. Prod. 0 100 200 300 400 500 fever cosine sim. Prod. Cosine sim. Prod. Cosine sim. Prod. 0.482 0.635 0.261 0.243 0.670 0.685 Table 10, Violin plots, 22, of document lengths for the top 10 retrieved hits and NDCG at 10 scores using a Distilbert base uncased model trained with either cosine similarity, blue, top, or dot product, orange, bottom, as described in Appendix H. 24.